Howdy. We hope to prove that we're team best team with this MXET 375 final project presentation. Before building our project, we created a design to test a vertical suspension system. The design for our system consisted of 2 springs and 2 masses. Attached to each of the masses would be an accelerometer to measure the acceleration of each mass. The masses would also be attached to a linear ball bearing system that would help guide the system. All of these components were found under our project budget of $70. Construction of this system started with a wooden frame that housed our linear motion system. The linear motion system was crucial in the design of this project as it held our vertical suspension system. If the system wasn't aligned properly, it would introduce more resistance to the ball bearings, creating faulty data. To test the system, we used 2 accelerometers on each mass and an Arduino Nano every. But to start the demonstration, we pushed the mass down to a fixed location, which is accounted for in our simulation. And then we released the masses, collecting the acceleration data.
For our project, we used 2 MPU 9250 accelerometers as the sensors for data collection, and our Arduino Nano every as the microcontroller interfacing with the accelerometers. Our program is written in C using the Arduino IDE and a library for the MPU 9250 developed by Boulder Flight. The main function used after initialization of the sensor module was the get function for the acceleration in the Z direction, and to print it to us in terms of meters per second squared. That data is taken from the terminal program from which it was printed to and transferred into an Excel sheet for analysis.
The first step in simulating the system was to derive the equations for it. These equations were derived with down being the positive direction and using a constant for the force of friction, Ff, which will later be determined through parameter estimation. The next step was to build the Simulink model, which can be seen here. Go to and from blocks were used in order to keep the model easy to read. After collecting our experimental data and running the parameter estimation, we were left with the following acceleration graphs. The estimated force of friction on each mass was about 0.613 newtons. While this is relatively high for linear bearings, the bearings we bought were very low quality and did not slide smoothly. As a result, this value makes sense. After running the estimation, the graphs of experimental and simulated acceleration match closely. There are a number of possible reasons for the remaining deviation in the graphs. Some of these include the polling rate we were required to use due to hardware limitations not being high enough and as a result not recording some significant data points, the possibility that our springs were fully compressed at the top of each oscillation, causing a hard stop that our simulation does not account for, and the fact that we did not simulate air resistance.
Thank you for watching, and this concludes our final presentation for MXET 375. Thanks, and gig 'em.